Yeah, now it's
Yeah, it's on. Okay, so after a few delays, we're ready to start the afternoon program. So let's welcome back Sasha Polishchuk, who will talk about supermoduli and supermeasures.
Okay, so the first result I'm going to tell about is about studying the behavior of super period map for supercurves near the boundary. Sorry, not near the boundary, near the divisor where spin structure acquires sections. So in some sense, in this super world, we should think maybe of boundary divisor as not only consisting of the supercurves which are not smooth, but also supercurves where the spin structure acquires global sections. In some sense, maybe we should think of this as part of the boundary. But anyway, so I will show that there is a natural equation for this divisor such that the superperiod map just acquires poles of order 1 along this. Okay, so first there will be some abstract setup. So isotropic intersection setup, which is mimicking the classical picture for spin curves which I outlined last time. And in this isotropic intersection setup, there will be some regularity theorem, and then I'll show how to apply this setup to the family of supercurves. So suppose we have a symplectic vector bundle or rather super bundle, so it can have even and odd parts. Over some base S, which is some super variety, and rank is it's going to be some even number of even dimensions and even number of odd dimensions. So remember, so symplectic. So it's even symplectic form, so if it's just purely even, then it will be usual symplectic form. If it's purely odd, then this would be a symmetric form. Okay? And so assume now that we have two maximal isotropic subbundles. So this will be isotropic subbundles of maximal possible dimensions. So they will both be, so rank and M, isotropic subbundles. And so I'll consider I can then consider I can measure their intersection by considering the following complex of length 1. So it's just L1 goes to V quotient by L2. And so this map is just induced by first embedding into V and then projecting to V mod L2. So it's actually, if you consider it up to quasi-isomorphism, you can see that, so it's up to quasi-isomorphism. You can view it symmetrically. You can just take here L1 plus L2 going into V. So the order of L1 and L2 is not important. On the other hand, you can also identify V mod L2 with L2 dual. So this is for any isotropic subbundle, you have the symplectic form on V induces identification of V mod L2 with dual to L2. So we can, if we view it this way, then we see that it's actually self-dual up to quasi-isomorphism. And let me call this differential D sub L1, L2. So I will assume that L1 and L2 are generically transversal. So, and L2 are generically transversal. So they have zero intersection. And I will be interested in divisor where they where they have non-zero intersection. So then I can define a rational section of a line bundle on S, which I will call theta of L1, L2. So this will be Berezinian of the differential. So this map D L1, L2, so away from the locus where they have non-zero intersection, it's an isomorphism, and we can take its Berezinian. So it's a global section of the line bundle. So we take Berezinian of L1 dual. And then the second line bundle is L2 dual, but Berezinian of dual is the same also as inverse. So here we'll have Berezinian of L2 also dual. So it's a rational section. So it's only defined away from the locus where L1 and L2 have non-zero intersection. And so the theorem, which tells you something more specific about the situation, is that, so assume an addition that for some point, if you take, so assume we're kind of living near some point where the even parts of L1 and L2 at this point. So once you restrict to a point, every superbundle canonically splits into even and odd part. So I take, so if I take some point S, I can restrict L1 and L2 to this point. So I'll call this L1S. This is a fiber of L1 at S. So this is a super vector space. It has plus and so even and odd parts. So I'll take intersection of even parts of L1 and L2 at S. And I assume that it's zero. So for some S. So then the claim is that near S, so we can trivialize our bundles, so we can just think of theta as a rational function. And the claim is that in fact it's regular, or rather its inverse is regular. So theta L1, L2, it's regular, and furthermore, it's a square of a certain regular function. Which is zero on the divisor where the intersection occurs. And also, this F serves as denominators for the inverse of the differential D. So D, of course, is everywhere regular, but if you look at the inverse of the differential, kind of, it's only defined a priori away from the divisor where L1 and L2 intersect. And the claim is that if we multiply by F, it becomes regular. Okay, so this will be kind of the abstract model which I will apply in the case of supercurves for appropriately chosen symplectic supervector bundle. And this condition will be satisfied kind of automatically. Right, so the idea of the proof is that you reduce essentially you reduce to purely odd case which is not surprising because we will kind of even parts do not intersect, so there is no problem with even parts. The problem is with odd parts. And in the purely odd situation, this is going to be the situation I considered last time. So where you have a space with this symmetric form, and you have Lagrange maximal isotropic there, and then basically when you consider when you kind of change maximal isotropic subspaces in a symmetric, in a vector space with vector bundle is symmetric form, then skew-symmetric matrices appear, and you can use Pfaffen to take square root of a determinant. So you use Pfaffens, and for the last assertion, you use the well-known fact that if you have a skew-symmetric matrix, then the Pfaffen kills the like if it's generically invertible, and if you want to take the inverse, so once you multiply it with Pfaffen, then this becomes regular. So this can be expressed polynomially in terms of phi. Kind of. Okay, let me now explain how to apply this to get a theorem about the behavior of superperiods of smooth supercurves near the locus where spin structures acquire a section. So application to supercurves. So this is still a story about smooth supercurves. So, if you remove the restriction, then the first statement certainly fails. So, but I think it is still true that if you just use the theta itself, yeah, I actually don't know whether theta inverse is still going to be regular. I actually not sure. I'm not sure. Yeah, this is actually a major question, whether theta inverse actually will extend regularly. I'm not sure it will. Yeah, so I think this is pretty essential condition. So, right, suppose now we have a family of supercurves over some superbase, so this is super variety, and this is a family of SUSY curves. So S, so family of supercurves, of smooth supercurves. So, yeah, so then such that generically, so for generic point of the base, if I take the kind of represent the corresponding supercurve in terms of usual curve and a spin structure, then the global sections of the spin structure is 0. But okay, this is true generically, but not everywhere, and we're interested in what happens at the divisor where this is not 0. So, yes, so I assume that there is a little more data. Maybe let me call by U. This will be an open subset where everything is okay, where spin structure doesn't have sections. So then I'll also assume one more piece of data which occurs Thank you. Yeah, where it's equal to 0. Yeah, this is an open set where it's equal to 0, right? So one other piece of data that I'll assume, so I assume also that we have everywhere over S, we have a Lagrangian subbundle in the corresponding bundle of H1s. Right, so we can take kind of sheaf of relatively constant functions, and it's R1 P star, so this is actually a local system. So it's just H1 of the underlying curves, kind of, and it's still a bundle over S with flat connection. Its rank is to G, where G is the genus. So it's purely even. This is a purely even bundle. So I assume that there is a Lagrangian's, yeah, and it's equipped with the natural intersection form, and I assume that there is a Lagrangian subbundle. So, for example, the theorem is local, so you can just locally trivialize this and choose a Lagrangian subspace in a fixed fiber, and then just spread it over the family. Right, so then on the other hand, over U, as I explained last time, we have this Hodge subbundle. We can take pi lower star of omega xs, and it is also a subbundle in. So this is another Lagrangian subbundle in this local system of H1s. So this is also Lagrangian subbundle. Okay, so this is only true over U, because otherwise the global sections will prevent for this to be a subbundle. And then I can apply this construction in purely even case. So I have a purely even symplectic bundle to Lagrangian subbundles. So I have some rational section. So maybe I'll go to the other board. So I apply this abstract formalism in purely even case, and I get theta of pair of Lagrangian subbundles, pi star omega x restricted to U and lambda restricted to U. And this will give me some rational section of some Berezinian line bundle. Okay, yeah, of rational section of determinant. I write determinant instead of Berezinian because lambda is purely even, and it's tensored with Berezinian of pi star omega. So here I'll write the Berezinian because I will then promote it to a line bundle on the entire S, and there I will need to use superstructure. So, okay, so now the theorem. So that locally we have same story as before. Let's for short write this theta sub lambda. So this theta is still a square of a regular function. So this is an equation of function. Yeah, locally it can trivialize all bundles and just view this as a function, and then yeah, this will be a local equation of the locus where spin structure acquires sections. And the second part is that so if if I have a Lagrangian complement to lambda, so if there is a Lagrangian splitting like this, so then any other Lagrangian can be written as a graph of some symmetric map. So pi star omega over u can be written as graph of linear homomorphism from lambda prime to lambda. Yeah, I forgot to say that this lambda, actually, these two, they are transversal on. So we assume that they're transversal on U. So this is kind of a period matrix defined in terms of this Lagrangian splitting. So typically, this is done, you kind of fix a symplectic basis in cohomology of the underlying curve, and this would be a subspace generated by A cycles. This will be subspaces generated by B cycles, so two Lagrangian halves. And then we define the periods as we look at the Hodge subspace and see how it is written in terms of those bases. Right, and now the claim is that, so now this period matrix omega, we can control its poles near the locus where near the complement to U, and the claim is that if I multiply with that function f here, then this will be regular. So it has order 1, at most order 1 poles along the divisory determined by the function f, which is precisely supported on this bad locus where spin structures acquire section. So at the first glance, it might look that this has very similar look as the previous theorem, but there is one catch. The catch is that here I assumed that L1 and L2 are defined globally. And here they're only defined on this open subset U. So I cannot actually deduce this directly from the abstract theorem. So what I have to do instead, I have to define another symplectic bundle, much larger, from which this one is obtained by some kind of symplectic reduction. And in this larger symplectic vector space, I will have a globally defined pair of Lagrangians such that the corresponding theta section will actually match this theta section. And so I will apply this theorem not directly to this symplectic bundle, but to some large one. And you may notice also that this symplectic bundle is purely even. So the larger symplectic bundle that I will need to consider will have both even and odd parts. Sorry, how is what related to what? Lambda prime is a complement, Lagrangian complement. So I assume, so I add more assumptions. Yeah, so I assume that also we have not only, so for part 1, I only needed one Lagrangian subbundle. Yeah, so actually this lambda is global, so this is defined not only over U. So yeah, so this one is defined over S. So the problem is that this one is only defined over U. So this is a subbundle. Yeah, so I assume that this is defined over U. Oh, sorry, over S. Yeah. Any other questions? Okay, let me explain how to define the symplectic superbundle for which I need to apply the abstract setup to deduce this theorem.
Could you explain again why this theorem does not follow from the other one?
Oh, because in the theorem, both Lagrangians have to be defined over the entire S. And here, only one Lagrangian is defined over S. The other one is not defined over S.
So the other theorem would give you a result over U, but not over S?
Hmm?
So the point is that the first theorem would give you a result only over U.
But over U, the result is trivial because over U, the section is invertible. So it doesn't give anything. I mean, the whole point of this theorem is that it tells you something about what happens on the local kind of. You want to go across this divisor where spin structures have sections. So if you're avoiding it, this statement is empty. Yes.
So now the question, so you also in the previous theorem you assumed that the even part of the two Lagrangians intersect transversely.
Yes.
So now are you saying the only question you're asking is whether what pushdown of omega has no odd parts?
So on over U, this is also purely even. Right. Because it sits as a subspace is something purely even. But of course, if you take some supercurve corresponding to the non-trivial to the spin structure with non-trivial sections, then this picture breaks down. So you will actually have some odd part if you try to calculate cohomology of this.
So you are basically asking when this odd part is not zero.
So I have to control what happens with odd parts. Yeah. So definitely, yeah. Yeah, and so the way I do this is we pick locally, we pick a section, so we pick a marked point. So this is well, sorry, no, actually not that. Sorry, I will still denote it as P, but it will not be a section, rather it will be a divisor. So it's given locally by one even equation. So locally, you can think of if you have relative coordinates z theta, then kind of P is given by z equals 0. So P is not isomorphic to S, rather this map has purely odd, it's a smooth map of dimension 0, 1. So it has one odd coordinate and no even coordinates relative to S. So we can always locally pick such a thing. And then I can, because it's divisor in X, I can look at conditions of kind of poles along P, relative poles along P. So I can define a bundle. So first I will define even larger bundle with degenerate symplectic form, and then I mod out by its kernel and get a vector bundle with non-degenerate form. So it will be degenerate skew-symmetric form, and then we mod out by the kernel. So I'll pick some n very, very large, and I consider functions with pole of order n along the divisor P, mod out by functions which vanish to a big order, but actually it's enough to just go to n plus 1. So functions which vanish up to order n plus 1. So if you locally, to see that this is a vector bundle, so locally there is a base corresponding to, so you have kind of sections like this. So I already kill z to the n plus 1. And also you have the same guys multiplied with theta. And so you see that it has equal number of even and odd dimensions. And so there is a natural skew-symmetric form on it. So the one you were asking about last time, so it's given by the residue at P of F delta G. So remember here, yeah, let me remind on this board what is delta. So delta is this analog of the RAM differential that we define using the superconformal structures. This is kind of structure derivation, which is given by in relative coordinates. Yeah, it vanishes on functions pulled back from S. And it kind of, in this local coordinates, it's kind of d theta plus theta dz applied to F times the basis of the Berezinian. And and the residue in terms of these coordinates is given by, so if you have f naught z plus f1 z times theta times dz d theta, so the residue of this is going to be, so the term without theta is just dies, so and here you just take the usual residue of f1 of z dz. Right, and so it's a skew-symmetric form because residue of delta of something is automatically 0, and so that implies a skew symmetry. And then the definition of my symplectic vector bundle is that you take V twiddle and mod out by the kernel of B. So this is a global definition. In local coordinates, I can actually precisely tell you what is the kernel of B. It's easy to calculate that kernel of B is just spanned by 1. So it's clear that, for example, instead of G, if you plug 1, then you always get 0. And a little less obvious is if you take the biggest one. So these two die out. So if you take z to the n theta, this one also dies out. So, and because of that, we get that the rank of V is something like 2n to n. So if we remove this one, then there are 2n even coordinates, 2n even elements and 2n odd elements.
Is there a slightly less local description of this kernel? I mean, this is written in terms of local coordinates.
The global description is the kernel of this form.
Right, but is there a slightly less local description of how to describe this kernel? Let's say in terms of seconds or something, or image.
Well, one is clear, just constant functions. Z to the n theta, of course, let's see. Yeah, I'm not sure I know any better way to say it than just this is a kernel of B. Yeah, because splitting into Z and theta, this of course depends on coordinates. Yeah. Yeah, it should be possible to say it just using the ideal of P. Yeah. Okay, now Right, so I have half of my setup. So remember, in my abstract setup, I need to have a symplectic vector space and I need to define some Lagrangians in it. So now in this V, I will define two maximal isotropic subbundles. And also I will need to explain how this V is related to the bundle of H1s. Right, so it is maybe also useful to observe that this V-twiddle, kind of using the differential, so using this delta, we can also, it's sometimes convenient to think of it in these terms, that you take, and maybe this already is going to be for V. So this is going to be pi star. So here we'll have sections of omega n plus 1 p, so sections of omega with poles of order at most n plus 1. And I put locally exact here, meaning that they're differentials of some rational function in terms of this delta. So locally delta exact. Well, this just means that they have zero residue. And then we mod out by omega of minus np. Yeah, so maybe that kind of that kind of answers your questions, how to give a global definition of V. So this kind of takes care of modding out by this kernel. Right, so yeah, so being delta exact is the same as having residue 0. Like in classical case.
Why is Z to the n back in the kernel? Why is Z to the n back in the kernel?
Z to the n
Without the theta.
without the theta is not in the kernel because it pairs with maybe this guy. I don't recall now, but I think it pairs with something. Yeah. Remember that you differentiate. Yeah, you don't just take a product. You differentiate one of them and then take a product. No, maybe just with z to the minus. No. Wait, with which one? Maybe just with z to the minus n, because this delta it produces theta even when you didn't have it. Yeah. Okay, great. So, right. So now, so one Lagrangian is actually easy. So one Lagrangian, it's just kind of one maximal isotropic. This is just we assume things to be regular. So this is going to be just pi star of kind of image of pi star OX modulo OX minus n plus 1p. So in other words, we just take in local coordinates, so we just take this part kind of to the right. Okay, so the other Lagrangian is a little trickier to get, and actually it will depend. So the second Lagrangian, second maximal isotropic, it will depend on this choice of lambda, which was a Lagrangian in this purely even Lagrangian in the local system of H1s. And to define it, I use the following exact sequence. So I have kind of, okay, so I consider kind of an obvious exact sequence. So relatively constant functions embed into functions with pole at most n, and then go into functions into the quotient sheaf. And this gives, so I take the corresponding long exact sequence of push forward, and then I get some map which I call gamma from pi lower star or x and p quotient by constant sheaf into R1 pi star cxs. And so the point is that, so gamma lives, so lambda lives here, and I can take its pullback, and then there's going to be a natural map from this to my v, and it's actually going to be a sub bundle of v, and I will take, I can view this preimage of lambda as a as a sub bundle in v. So namely, again, using delta, I can identify pi star of O and P modulo constants. So this is just going to be pi star of locally exact forms with pole of order at most m+1. And of course, from here we have an obvious map to V, right? So V is determined in terms of this quotient, so therefore it induces a map on pi star. And so the second Lagrangian is defined, so the second Lagrangian L sub lambda. So this is L canonical, that's the first one. The second one is L sub lambda. It's defined as image in V of gamma inverse of lambda. So gamma inverse lambda lives here. Now there is a kind of key fact that so we have on this pi star of Ox and P modular constants, we have from it two maps. We have one map to V and another map to R1 P star of Cx. Yes? So to the local system of H1s, and both of these have some symplectic form. So this has a symplectic form B, and this has a symplectic form, kind of topological pairing. And the claim is that the pullbacks of these symplectic forms are the same. So this is actually not surprising. Let me just mention the related classical fact about kind of relation between this residue form and the intersection form on H1. Okay, so this is, so the proof of the key fact is similar to the classical fact. So let's say if you have a usual curve with a point, then there is a identification of complex cohomology H1 with the space of kind of, you take global differentials, possibly with pole at this point, and you mod out by exact differentials. So you consider, yeah, so if there are more than one point, you consider kind of locally exact differentials of the second kind, which are meromorphic differentials with no residues at these points. But when there is just one point, then the residue is automatically zero by the residue theorem. So you consider this quotient, and so we have a kind of easy, kind of classical identification like this. Then here we have the yeah, we can also kind of rewrite it in terms of this residue form, and here we have a classical intersection form. So, okay, so if I have a form here, kind of an element here represented by some form, so in a neighborhood, so if I have a class here, in a neighborhood of this, of point P, we can write eta as a differential of something, right? And now if you have two forms, so you can write both of them as differentials, and then this residue of Fi df, F1 df2 becomes a well-defined symplectic pairing on this space. And the claim is, so if you denote this map as C, so the claim is that if you take now topological pairing between the classes in H1, then it's precisely equal to this residue pairing here. So this is a classical fact about curves, and so our statement is a kind of super analog of this, which is proved in a very similar way. Right, and then after we've done this setup, then the theorem actually follows pretty easily, because the claim now is that, so this so this data V with L canonical and L depending on lambda, so it's kind of related to the, so if I restrict it to U, consider over the open U, then it's going to be related by some kind of, so from it, by applying some symplectic reduction, which means that there is some, so there is, okay, the symplectic reduction will be as follows. So this, there's going to be some non-maximal isotropic subspace I, such that this lambda sub lambda lives inside I orthogonal and contains I, and then you take kind of I orthogonal modulo I, and you get a new symplectic space, and from lambda canonical you get a second maximal isotropic subbundle there. So from symplectic reduction you precisely get this bundle of H1s with the subbundles. So the first one will be a pi star of omega, and the second one will be lambda. So, and one can check that this construction of the function theta is actually preserved under this reduction. So whatever I prove for this function here will also hold here. And then here I just apply my, apply the abstract result. So apply this isotropic intersection theorem. Okay, so again, the difference was that here all of these guys actually make sense globally. So this, okay. So this is probably a good moment to take a 5 minutes break, because after this I'm going to talk about superstring measure and what this result gives for its regularity. I felt too good. Yeah, we're never interested in going far away from diagonal because we just need to, in some sense, we want to integrate over some cycle on diagonal, which, well, it's a little lie. So you actually need a little more than diagonal. So this kind of, you want to consider pairs of spin curves with the same underlying curve. So there's going to be something called quasi-diagonal, but kind of everything that we can pretend that it's just a diagonal, and kind of the partition, the amplitude that we want to obtain in the end is going to be by integration over diagonal, so therefore we don't need to worry what happens far away. But we do have to worry about the fact that instead of the moduli space S, we just have this open set U that we throw away bad supercurves. So now let's try to put them back. So theorem is that if genus is at most 11, then mu extends regularly near diagonal in S times S conjugate. Okay, so the proof, so it's going to use this isotropic setup and the theorem I proved earlier about the behavior of the periods. So the periods come into this story, of course, because of this determinant of H. Because if you kind of locally write this H, then it can be written in terms of the superperiod matrix. So, right, so first of all, we can view, so kind of near diagonal, we can identify the, remember we had this symplectic bundle of H1s, and we can kind of identify its pullback from the first factor or if it's pullback from the second factor. If the curves are either the same or at least close to each other, we can identify their H1s. It's kind of using the and therefore, we have our kind of over U, we have our subbundles F. And so here we have P1 star of F, and here we have P2 star of F bar. So we can view them as sitting inside the same symplectic bundle. And then it's easy to see that this determinant of H inverse, which I wrote over here, it can be expressed in terms of this isotropic intersection setup as theta of these two, actually theta inverse of these two maximal isotropic subbundles. Okay, so this is defined as kind of as in the isotropic intersection setup. And this determinant of H inverse, this is actually the main thing we need to understand, because psi times psi bar makes total sense everywhere on S times S bar. We have no problem with the Mumford isomorphism. It is defined everywhere. So we just need to prove the statement about extending to holomorphic section defined everywhere near diagonal in S times S conjugate. We just need to do it for this guy, for this determinant of H inverse. Okay, now we need to throw in some extra Lagrangians. which are defined using some real Lagrangians in this local system. And then we'll need to use our regularity theorem. Okay, so we're going to study this function by actually mixing in some kind of by studying its relation to similar functions with respect to the third Lagrangian here. Okay, so we are going to assume that. Okay, so we're going to fix some real Lagrangian splitting. Yeah, so we're always working near some point of the diagonal. Near this point in the diagonal, we can fix some Lagrangian splitting of R1 pi star C into, let's call it W and W prime. And then, actually, yeah, sorry, there is inverse here. So then, actually, we know something. We know something about theta of P1 star F and W. So kind of using our general, and actually about the second one as well, about this one. So this we know from this isotropic intersection theorem, because okay, and okay, well, maybe this is a little imprecise, so I will not say, I will make it more precise. And then the idea is that there is some abstract equation you can write which relates this theta and these two thetas. Okay, and then some determinant of the period matrix will appear. Okay, so there is a kind of general fact in this isotropic intersection setup. So if you have this splitting of super symplectic bundle into Lagrangian halves, and you also have two extra Lagrangians, lambda L1 and L2. So these are all Lagrangians. This is Lagrangian splitting, and L1 and L2 are generically transversal and generically transversal to W. So then you can write each of them, you can write as a graph of a map from W prime to W. So if we apply this to this Hodge subspace, Hodge subbundle F, we'll get precisely, in one case, and its conjugate, and we'll get precisely the period matrix and its conjugate. And then the general formula is that in this case, theta lambda 1 lambda 2 is equal to theta lambda 1 W times theta lambda 2 W times the Berezinian of the difference, tau 1 minus tau 2. Well, in our case, this will be determinant. Okay, this is a purely formal calculation. So in our case, we apply this to L1 equals P1 star F, L2 equals P2 star F bar, and we get this function which we want to prove extends regularly is written as product of three functions. So fw inverse, theta f bar w inverse, and determinant of tau minus tau bar inverse, where this tau is essentially the superperiod map, almost. So there's some, yeah, I will say what it is. So, and then from earlier we know that this guy is going to be a square of this holomorphic equation for the divisor. So f equals 0 is equation of the divisor where spin structure acquires a section. So this is going to be f bar squared. And so we need to analyze this guy here. And this guy here can be written as follows locally. It's going to be a classical period matrix plus something which depends on odd coordinates. So this will be classical period matrix. And this will be, okay, so because it's an even object, so the odd coordinates, they have to come in pairs. So it will live in the square of the ideal generated by odd coordinates. So n is the ideal generated by odd coordinates on the moduli space. And from the previous theorem, we also know that tau has a pole at most of order 1 along f. So f times tau is regular. And now we can finish the proof. So the function that we want to analyze is actually not this function, but its fifth power. Right? So we need to analyze this determinant of h to the minus fifth. So it's going to be fifth power of everything I have here. So it will be f to the 10 times f bar to the 10 times this determinant of tau minus tau bar, where tau is equal a plus omega, where omega is a classical period matrix of the underlying usual curve. And omega lives in n square, and it has pole of order at most 1 along f equals 0. So omega is written like this. So now the statement we want just formally follows from this. So you just look what kind of poles this kind of guy will have, and when you kind of have regular functions and then you generate a subring with functions of this form, kind of n square over f, then you will have kind of expressions like this. And so now if you see, so up to k equals 10, they're going to be killed by this product. So the first thing that will not be killed is when you have n to the 22. So this is the kind of smallest power that can appear here that is not killed by this. But if genus is at least 11, so then the odd dimension. So the odd dimension of the modular space. Okay, so I forgot to say that S dimension of SG is 3G minus 3 even dimensions and 2G minus 2 odd dimensions. So then sorry, if G is less than or equal than 11, then 2G minus 2, the number of odd dimensions, is going to be definitely smaller than 22. So therefore, n to 22 is going to be 0. So the terms that possibly do not possibly acquire pole, they're just zeros because there are too many odd coordinates in them. Okay, this is maybe a good place to ask questions because I'm going to switch gears after this and start talking about about stable supercurves. Yes?
You gave us L1 and L2, but you didn't quite say W, but maybe
I said before, we fix Lagrangian splitting, real Lagrangian splitting.
right, but so I guess you didn't want to talk about why is tau related to, A related to the classical period map.
Just because when you mod out by odd coordinates, you get the usual period. The only statement here is, yeah, I kind of use something obvious. So yeah, it's not serious here. Yeah. Because I want to remember in this isotropic setup, I need to know that the even parts do not intersect. And when I take even parts, I will get classical Hodge subspace. And the classical Hodge subspace in H1 never intersect any real Lagrangian. Yeah, if you take an H1 of classical curve, you take Hodge subspace and you take a real Lagrangian. They never intersect, they always intersect by 0. I'm using this classical fact. So this is needed in order for the isotropic setup to work. Yes? We haven't done any calculations in higher genus because we were too carried away with working with stable supercurves. But this is definitely the next step to look at. But
So you don't know that it is or it's not working.
I don't know. Maybe there is some, but it's certainly not kind of going to work with this type of reasons. So maybe there are other reasons. Okay, so now I'll start talking about stable supercurves. So of course, because in the end we're interested in integrating this superstring measure, so it's not enough to know that it's regular on the space of stable, on the space of smooth supercurves. So because in this integration, we'll need to know whether there are any divergences at the boundary. And in fact, there are divergences at the boundary. But somehow, the claim is that you can regularize the integral and kind of get rid of them. But this is a long work, and we are kind of working on this in genus 2, and it's almost over, but there are many, many steps. So I will probably just tell you about some of the beginning steps. And of course, the first beginning step is just discussing what are stable supercurves. So let's first discuss, as in the case of smooth supercurves, let's first discuss what, without considering families, just what it is if we just have one such stable curve. So it should be there should be an underlying. Okay, so what is a single stable supercurve? If you like, absolute case. So this is going to be no longer a super variety. It's going to be a super scheme of even dimension 1. Yeah, for super scheme. Yeah. So the corresponding Bosonization is just going to be the usual curve. So if you kill all the odd variables, you get usual. But C, of course, is allowed to be singular, so it should be a stable curve in the sense of Deligne-Mumford. So for now, the full stability is not important for me, just the fact that it has nodal singularities. So nodal. That's the major thing for me. Yeah, the fact that stable so you also need some global condition, but let's skip it for now. So now the structure sheaf of X, so it should have even and odd parts. So the even part is just functions on this underlying stable curve, and then there is some odd part which I will still call L, and L will be you can think of it as a coherent sheaf on C, so it's going to be what is called a generalized spin structure. Namely, it's a torsion sheaf, torsion-free sheaf of rank 1 on C. Yeah, and I will tell you exactly how it can look locally. So we're equipped with isomorphism. So there should be an isomorphism of L with sheaf home from L to the dualizing sheaf of C. So this is a generalization of an isomorphism of in the spin structure we had an isomorphism of L square with omega C, right? But kind of on the smooth locus of C, L is also going to be smooth, and you will just have an isomorphism. L will be a line bundle, and you'll have an isomorphism from L to L inverse tensor omega C, which is the same as the usual spin structure. But near the node, something interesting happens here. Let me explain what can happen near the nodes. So, by the way, the modular spaces of kind of generalized spin structure appear when you want to compactify this classical modular space of spin curves. And this compactification was constructed by Kornalba and also by Jarvis. So they give different descriptions of moduli functor, but the modular spaces turn out to be the same. So Kornalba actually uses different description than this one. This is a description due to Jarvis. So node kind of formally locally looks like kind of is described by the ring. So you kind of have variables x, y, which are variables on both branches, and then you make an equation xy equals 0. So now you can just study what are possible modules over this ring, and in particular you can study what are torsion modules. Let's call this ring R. So there is a classification of torsion-free modules over R. So in fact, there are 3 types of indecomposable modules. So every torsion-free module over R is a sum of modules of 3 types. You can have a free module, you can have R modulo X, or you can have R modulo Y. So now if you require that on a smooth locus you have rank 1 torsion-free sheaf, then this will not work, or this will not work because they have rank 1 on one branch and rank 0 on the other branch. So if you want rank 1 on both branches, you need to add them up. So then you have 2 options. Either it's a free module near the node, or it's R modulo X plus R modulo Y, which is, by the way, isomorphic to the just maximal ideal in this ring. because the maximal ideal in this ring, you just consider either series which only depend on x or series which only depend on y without constant term, then they split into direct sum of two pieces. Right, and so this, when we have a generalized spin structure, we can look how it, we can look at it near each node. So if we have L as a generalized spin structure on a stable curve, on a nodal curve, so for each, so if you take this pair L and a node, so Q, so let Q be a node in C, then it can be of one of these two types. Either L can be locally free, and then, so if L is locally free near Q, then we say that this is a Ramon node for L. Or it could be not locally free, the other case. And then this is called the Neveu-Schwarz node. So you can further say maybe what happens in terms of normalization if you resolve the node. So yeah, when so they will actually, so there are also conditions on the punctures you can consider. So when you consider supercurves with punctures, there are punctures of two kinds as well. And so when you glue stable supercurves by identifying punctures, if you identify two NS punctures, you'll get an NS node. If you glue two Ramon punctures, you will get a Ramon node. Yeah. Say it again.
If you identify two of the same type, you get Schwarz.
You cannot identify of different types. I don't think. Sorry? Okay, let me tell you about what happens when you have normalization. So suppose you have, just suppose for simplicity, C has one node. So then we can consider normalization of this node. Yeah, suppose L is generalized spin structure on S on C. So, right, so then you have normalization map. So basically, yeah, you kind of, you uncross the two branches. So the pullback of the node is going to be 2 points here. So there's 2 points which are glued into this node. Let's call them P1 and P2. Right, then as well known, so if you take pullback of the dualizing sheaf and the normalization, you will get dualizing sheaf and C-twiddle, but twisted at these 2 points. So now what happens in these two cases? So in the case when L is Neveu-Schwarz at the node, then one can see easily that this L is obtained as push forward of spin structure. So G is the usual spin structure on normalization. Now, in the case when L is, and in other words, so the punctures here are just the usual punctures. There is nothing special going on there. These punctures P1, P2 on the normalization. Now, if L is Ramon, if it's locally free, so then the pullback of L it's going to be, let's call it L twiddle. So it's going to be again a line bundle on C twiddle, but it's not going to be, so it's not a usual spin structure on C, but it has, you have to twist the canonical bundle on C by these points P1 and P2. And that's exactly what we call kind of punctures of Ramon type on smooth curves, smooth supercurves. Okay, so now I can give a global definition of families of stable supercurves. When do I need to stop? Is there an official time? Or maybe 5? I'm definitely not going to stop earlier than 5. I can spend about 10 minutes. Okay, I'll think about it. Okay, so maybe I'll just have time to say something about definition and formulate a theorem. And I won't go into details of deformation theory for now. Right, so definition of stable supercurve, which is due to Deligne. Okay, so stable supercurve in the base, in the family, X over S. So where S is any super base. Yeah, this is due to Deligne. Okay, so this should be a kind of flat family of super manifold, of super variety, of super schemes. So it should be a flat morphism. Now, obviously, we want any kind of fiber over any geometric fiber should be a stable supercurve as we defined before. But there is something, so yeah, there is some extra, okay, maybe I'll, so yeah, so this structure of stable supercurves here on each fiber, it's induced by certain global structure here. And so the global structure that induces this is this derivation, delta. Okay, so this is defined globally for this entire family. So here, omega xs is a relative dualizing sheaf, and it's not necessarily a line bundle, and it is kind of well defined because we make some assumption on the singularities of the fibers, which is kind of here, kind of follows from this, from what I said in this case of just absolute stable supercurve, right? And so we want that this derivation kind of induces the structure. Okay, so maybe I'll say it like this. So there is a so if you throw away the nodes in the fibers, so if you take kind of fiber-wise dense open, such that with this structure, omega u over S is a smooth supercurve with this structure derivation delta. And yeah, one more condition is, well, it's kind of contained implicitly here, but it's maybe nice to point it out. So for any geometric fiber, xs. If you look at what happens, kind of what kind of map it induces on the odd parts of the corresponding sheaves, then it actually becomes an isomorphism. Yeah, but this is actually already contained implicitly in my description of stable supercurves over a point. So you can forget about this. So there is a local description of how this should look like near the nodes, but maybe I'll skip it for now, and I'll just tell you the general theorem. Okay, so the general theorem is that there exists a modular space. So if we consider SG bar, so this will be a stable, kind of stable supercurves. So as before, we only restrict to, actually here it's not important. So L could be even or odd. So stable supercurves, so they form a nice modular stack. So it's a smooth, proper Deligne-Mumford stack. So I think this is also known as orbifold. So it's almost as good as the usual smooth proper variety, but so the fact that the stackiness has to do with the fact that we have to take into account automorphism. So locally it looks like some smooth superspace mod out by a finite group. Okay, so yeah, there is kind of, so yeah, I will probably make some comments on what goes into the proof. So for example, it's crucial to study some deformation theory of stable supercurves, maybe one of the most crucial ingredients. But I think this is actually a good point to stop for today. So next time my goal will be to tell you what happens with Mumford isomorphism near the boundary of the modular space. So I will also maybe define, I will also explain how Mumford isomorphism is constructed for smooth supercurves and how it behaves, what kind of poles it acquires near the boundary where the curve stops being smooth. Okay.
Questions?
Yes, there is a local description of delta near the nodes, yeah. So you mean in the case when S is a point, it's going to be especially easy, but it will be different for two cases. For the case of kind of Niva-Schwarz and for the Ramon case, it's given by.
But I can ask you later. You don't have to.
It's unfortunately there are some notations I have to introduce. I'm not going because you need to kind of you have these two branches. So you need to kind of.
I can ask you later.
Yeah.
Anyone else? So let's thank Sasha.